My name is Wendy Dombrowski. First, I'd like to introduce our moderator. He is Nardo Manaloto, a technology executive with extensive experience in deep tech, corporate innovation, and startup acceleration with Catalyze. He is also general partner for Qubits Ventures, a pre-seed fund investing in quantum technology startups. I've already posted his links in the chat, and I can reshare that once everyone arrives. With that, I'm going to turn it over to Nardo.
All right, thanks, Wen. Welcome, everyone. I'm glad you guys are able to join our quantum event here. We have a really exciting speaker from QCware, so I'd be happy to introduce him to you. Yianni Gamvros is the head of product strategy and business development at QCware, where he is responsible for the company's product direction, business partnerships, and sales. He began his career as an optimization solutions consultant at iLog, which was acquired by IBM, and then became part of IBM's sales leadership team, covering products in AI ML, optimization, and predictive analytics. He holds a PhD in operations research. And I've known Yianni for a while now, and he definitely knows his space. So I'm glad to welcome Yianni here to this event. Yianni, take it away.
All right, thank you so much. Thanks, Nardo. Thanks, Wen. Thanks for the introduction and giving me the opportunity to chat here with everyone. So we'll be talking about quantum computing, and I'll give you a little bit of a perspective on why effectively it's interesting, and let me just make sure I'm picking the right screen. Okay, you guys should be able to see my slides now. On why it's interesting, why it's powerful, and why essentially we need to get ready for it. And what can you do essentially to get prepared and get your organization prepared. So I'll try to keep this short and have plenty of time for questions in the end, but please start asking questions, start posting them essentially in the chat, and then we'll get to them at the end of the presentation with enough time to hopefully answer all of them. Okay. So first of all, I think the key question we need to answer is why quantum computing, why we should be even interested in it, why get ready for it, why engage in it right now. And the answer to that is actually quite simple. It's because it's essentially data science accelerator or data science on steroids. Pick your favorite essentially tagline. But everything we do today with data science, machine learning, AI, optimization, simulation, quantum computing holds the promise of essentially getting us either faster results, faster solutions, or better solutions, right? So sometimes I say this, I present the slide and I say all these words, and it's still not clear, obviously, to people how much faster quantum computing can be over classical, right? So let me give you essentially two more tangible, more concrete examples of how much more faster quantum computing can be over classical. So the first example is this very simple example. Let's say you're looking for a certain value in this array. Let's say you're looking for a certain value in within a number, let's say, of records, and these records are completely unstructured, completely unindexed, and therefore you would have to do what anyone can think of at the top of their head right now, which is basically to go essentially one by one. Remember, there's really no information about these records, so you have to go through each and every one to search for the right for the one value that you're looking for, right? And as a result, let's say if you have 1 million records in here, the worst case scenario is that it's going to take you 1 million steps to find the one value out of this array of records. So you're basically going to be doing this brute force search, right? Which can take, a significant amount of time in the worst case scenario, right? So this is a pretty kind of standard problem. I mean, there's no kind of trick questions here. However, if you essentially take this same problem and move it into essentially a quantum computer and apply a known quantum algorithm to solve it, then you can do the same thing in 1,000 steps. And this shows you already how quantum computing is essentially fundamentally different from classical computing, how it's counterintuitive. This very standard problem with a very standard solution on the classical side has a very different answer on the quantum computing side. And this answer actually can be significantly faster, right? And this algorithm actually has been known for quite some time. I think Grover actually came up with this back in the 80s, right? And it actually served as one of the key motivators to do more research in quantum computing and actually figure out if we can actually build these machines. The fact that Grover was able to prove back in the 80s that quantum computers will have essentially this significant performance advantage over classical computing. So this is essentially one example, and I use it because of this its historical significance, but it's a little bit abstract, right? I mean, no one is searching kind of for this one value in this array of, unstructured and indexed data. I mean, this problem is not really very sort of practical, doesn't have like this tangible feel to it. So we can go to a much more tangible and much more contemporary example. And there are these systems called recommendation systems. Actually, you interact with them pretty much every day. I can assure you that everybody on this call is interacting with some kind of recommendation algorithm, data science algorithm, machine learning algorithm every single day, right? So these are the systems that that essentially come into play when you make a purchase, let's say on Amazon or your favorite retailer. You get all these other recommendations of what are the other things that customers like you would typically buy or have bought, or that you will be interested in as well, right? So that's one type of recommendation system. You're probably even more familiar with them if you're interacting with things like, which I'm sure like everybody you are, things like, for example, streaming services, like video streaming services like Netflix, or audio streaming services, which actually for audio streaming services, you get served a song right after the song you're listening to ends. You get served another song and another one and another one. And if you're not maybe listening to a specific playlist, these things essentially get get generated by a recommendation system like this. Same for Netflix, right? When you open up Netflix and it serves the initial page and it makes recommendations on what's the next thing that you're going to like watching. It's the same kind of system, right? And what the graphic that I have here kind of shows essentially maybe the size, potentially the size of the problem that we have to solve, right? So you have 100 million users, or maybe tens of millions of users, and maybe tens of millions or 100 millions of products, right? And these blue boxes here represent the fact that, each of these users obviously have watched some of the movies or bought some of the widgets, right, that this retailer is selling, and maybe they like only some of them. So the blue boxes represent essentially their preferences, what they like, right? And the challenge of this recommendation system is that when a new user comes in, then based on this information, this very sparse information on what the previous users liked, this system has to make a recommendation on what this new user is going to like. And people already kind of figured out how to do that on the classical side. And even though each and every one of us think they're pretty unique, it turns out, once these data scientists actually run this on systems like Amazon's system or Netflix or Spotify and all these things, they kind of figured out that, hey, look, not everybody's really unique, but there's like a few a dozen archetypes. I think, on average, they find that there may be like 80 or so archetype users, and everybody's basically one of these 80, has one of these 80 personas. And so, whatever if we can match you with one of the existing personas, then we can recommend pretty much things that, we know you're going to like, right? But these things actually take time, right? Even on a classical system, even on things like GPU farms, right? Training a neural net that will actually be able to predict which one of these 80 personas you are, and then therefore actually make additional recommendations. It takes 1 trillion steps, right? That are executed very quickly but can still take actually days and sometimes weeks when they're running on GPUs, right? Okay, so this was a pretty long-winded story, but this is the punchline right now. So it takes 1 trillion steps on the classical computers to actually train the neural net to do this. And you can maybe write down how much you think it's going to take on the quantum computer, and whoever gets closer, I'll buy them a beer. And next time we meet somewhere, maybe in Pasadena. If you guys are local to Pasadena, maybe somewhere in Silicon Valley. I'm based there. But maybe write your number down, and whoever gets closest, I'll give you a second here, and then, or you can put it on the chat. Easier. We don't have to do video. So I'm going to wait here. Let's see, people putting on their chat. Yeah, I can see people. Yeah. 42, always a good answer. 1, kind of, yeah. Okay. Okay, pi, yeah, always a good answer as well. Yeah, okay, good. So here's the answer, right? So the answer is 1,000 steps, and I think actually someone actually said exactly 1,000, which is kind of a lucky guess, I'm sure. But or someone has seen my presentation before. But David, I guess David Tur, yeah, I owe you a beer. So so definitely email me next time you're in around the San Francisco Bay Area, and we'll definitely do that. But you also see kind of the huge performance differential between classical and quantum, right? And obviously the next kind of big question that you might be asking now is, okay, well, how come? Like what's what's under the hood that makes it essentially go this quickly, right? And obviously that's a huge that's like not a 40-minute lecture, but that's, I think, like a graduate course in quantum computing, right, to really understand why. But what I'm going to do now is just explain the why in just one slide, which is kind of the qualitative why quantum computers are going to be much faster and going to provide results much faster. I'm not going to go into the details in quantum entanglement or superposition, any of that stuff, or how qubits work. I'm just going to show you essentially this graph. It's all about this graph, which really talks about how classical computing scales with respect to problem size and how quantum computing scales with respect to problem size. So as the problem size grows on the x-axis, the time to find a solution on the y-axis grows essentially in some cases exponentially, in some cases just unfavorably with the problem size. However, for some problems, again, quantum computing, it's not like you can solve any problem in quantum computing, but for some problems, the scaling is actually much smoother on the quantum computing side. And that's why essentially everybody's very excited about this technology, and this technology has the potential of very significantly essentially disrupting what we do today with data science and machine learning, optimization, simulations, those specific problems where this scaling, essentially disparity, comes into play. And to go back to what I showed earlier in terms of like faster solutions or better solutions, you can use essentially this disparity in scaling to your advantage. You can essentially solve the same problem, but the quantum computer is going to be much faster if we solve the same problem. Or you can actually solve a much larger problem that has more granular information, and where you can get a much better answer. Okay, so it's not just about faster answers, it's also about better answers. And as I said earlier, quantum computing is not here basically to replace all other forms of computing. It's essentially just another version of a hardware computing, of a hardware processing unit that will essentially give us a way to solve certain problems better, right? Just like we have GPUs and they're good for certain things, FPGAs are good for other things, ASICs are good for other things. Therefore, in the future, we're going to have quantum processing units, QPUs, that are going to be good for certain things. Okay, so keep that in mind. So the next thing you might be asking, okay, well, show me some applications where we can use this performance, right? And in a nutshell, these are the quantum computing applications that quantum computers will be really good at. And this differentiation basically in scaling will come into play, and quantum computers will be great at solving these types of problems, right? So there are quite a few problem types here. So I'm going to start from the left. There's this very specific thing called certified random number generations. It turns out quantum computers are great at producing random numbers. And actually, the only reason I'm putting this application there, even though it's not really like a very generic application, is because that's what that Google supremacy experiment that you might have heard of, that's the application that essentially helped Google prove that their quantum computer could do something that a classical computer could not do. Okay, so it's kind of very specific, very narrow, but there are some other things here that are actually very broad. Things like chemistry simulation. So we can use quantum computers to simulate molecules and use that knowledge to then produce those molecules into the lab, knowing how they will behave in advance, and then take those molecules, either if it's a drug molecule, take them to patients. If it's a materials molecule, take them to the appropriate application for that material. So, so quantum computing will revolutionize these two fields, drug discovery and material design. So there are other use cases here, or there are other problem classes here, like binary optimization, which is something that comes into play in supply chain and manufacturing and scheduling and transportation. There are things here like differential equations, obviously things like machine learning with all of its applications like imaging, image recognition, natural language processing, classification, regression, all these things. And there are things like Monte Carlo methods that are used for risk assessments and other interesting problems in finance. And then convex optimization, essentially kind of a more generic flavor of binary optimization. So some things require certain types of convex optimization problem classes, and it's similar, but it's a little bit different from binary optimization. I'm not going to go into the weeds. Okay, so this is basically these different problem classes that quantum computing will be very good at. So you might be saying now, okay, well, show me some of these things in practice, how they work in practice. Show me, for example, a chemistry simulation in practice on a quantum computer so I can kind of see the whole thing, right, end to end. Well, unfortunately, that's not possible today. And the reason why is that, remember this graph? Right, so this graph is kind of great towards the right-hand side of the graph where the problem size is large. Unfortunately, right now we're not there. We cannot get towards the right-hand side of the graph, because that means that we would need to be able to solve a large problem on a quantum computer. Right now, the quantum computers are pretty small. So we're sort of on the left-hand side of the graph where that orange rectangle is. So if we zoom in there and kind of see what is happening, where are those lines in that rectangle, we're going to see this picture, which is kind of this essentially relation of the classical to quantum is kind of reversed from kind of the macro picture we were showing earlier, right? And unfortunately, right now we are in this situation where classical is faster. And really the reason classical is faster in this case for very small problem sizes is because the scaling has not really kind of taken into effect. And we've been essentially polishing and engineering classical systems for the last 50, 60, 70 years, right? So classical now has this kind of significant step up on quantum for these smaller problem sizes. Okay, so you might be asking then, okay, when are we going to get to the crossover point? When are we going to get to this situation where quantum actually becomes faster? And the answer is this, right? So for different applications, it's actually, the answer is different. And for, as I said earlier, these certified random number generators, we've actually already done that. I mean, the Google experiment, the Google supremacy experiment was actually based on exactly that. So in some ways, it's already been done. We're already there. For things like chemistry simulation, we're going to get there in 2 to 3 years. And for things like optimization, machine learning, and pretty much everything else, it's probably going to be closer to 5 years or more. So now I know this is a huge kind of letdown in the sense, okay, I mean, you kind of fired us up with quantum computing and all the great things that it can do. And now you're telling us it's like a few years away, right, for interesting things. So why should why should your organization be interested in it right now? That's the other big why that we have to answer, right? And the answer to that is this. It's basically the same answer, because data science, again, it's going to be quantum computing is going to be data science on steroids or data science accelerated. But when we said that earlier, we kind of said, okay, that's a good thing. It's a huge ROI, huge, potential, but it's also like a very scary kind of proposition, right? If you think about it, because everything potentially in your organization today that runs on machine learning and AI and optimization and simulation, will essentially have to be kind of rewritten. Like you will have to find new vendors, new data scientists that know about quantum computing. You'll have to kind of rework essentially the algorithms, the applications, the processes that take the data, process it, and then spit out results. And you have to kind of essentially rework all your digital transformation initiatives, that the things that, have taken you essentially 5 years to set up now, once kind of the whole ML AI revolution came into place. You'll have essentially to rework that for quantum computing. So that's why it's scary, and that's why there's a scary storm basically on the horizon, because it has the potential of essentially bringing forward this huge disruption, both for organizations, but also on the personal side as well, right? I mean, there are people that have essentially dedicated their lives to learning about, data science and, the different algorithms and becoming experts. And all of a sudden we're telling them now, well, hey, look, you can't even solve a simple search problem as fast as the quantum computer can. You need to kind of figure out how to code a quantum computer to be able to do that, much, much faster than what you've learned basically all these years and have been doing kind of all these years. So effectively, the reason why we need to engage, why you need to engage in a quantum computing project today, is effectively the same reason you buy insurance, right? So it's going to be your quantum insurance policy. This engagement into quantum computing will let you know what are the key problem classes that will be affected, what are the real use cases, and it will also help you start building skills. Engaging in a project today will help you start building these skills that are going to be much, much valuable when quantum computing essentially gets there. And sort of this is the premium that you have to pay, right? This is kind of the insurance premium that you have to pay in this kind of quantum insurance policy. You start putting in the time now, a little bit at the time, and you start building skills early. And then you kind of transform and kind of this whole idea of like having a data science team and data scientists and hiring and training them and retaining them, which is kind of very hard today. All of that essentially is going to kind of repeat itself with quantum engineers. Okay, so you might be asking now, okay, well, this is not where I expected this to be going. Is anyone already doing this, or am I going to be the first one basically to be doing this? So good news, there's actually plenty of industries that are already essentially catching up on this, catching up on the fact that yes, quantum computing is not going to be ready for production in a few years' time, and therefore I have a few years' time to get my workforce ready for this quantum computing future. So let's look at who's engaged today. So the names that I'm going to present today are essentially from the industry collaborations we as QCware have executed. So these are the names that I'm familiar with and I can talk about. There are many, many other companies in many of these sectors that are engaging other vendors and are building quantum computing teams on their own. But these are the examples that I feel comfortable obviously discussing. So big finance players like investment banks, and specifically Goldman Sachs, is actually building a big team that's dedicated just to quantum computing research and understanding how they are going to be able to use it for different problems within banking. One of the key problems is actually derivative pricing, right? This is one of the key problems because pricing kind of complex derivatives and complex portfolios takes a lot of time using this technique that is Monte Carlo simulation, right? You have to run a lot of different simulations and you end up with a good estimate basically of what the price is going to be and a confidence interval around that price. And what typically happens for very complex portfolios and very complex assets is that these calculations also get executed on GPUs, on data centers, but they happen once overnight because it typically takes hours to run these things, right? And therefore, there's essentially one price that the analysts and the traders get in the morning from the overnight run. And ideally, these banks and these investment banks want to enable their traders and their analysts to essentially get more recent information, to get information on what the appropriate price is based on what is happening through the trading day, especially for a volatile trading day, right? So the thinking is that quantum computers will be able to price these, will be able to run essentially Monte Carlo simulations much, much faster, right? Anywhere from 10 to 100 times to sometime in the future, maybe 1,000 times faster than what classical computers can do today. And therefore, we'll be able to actually do some of these runs during the trading day when when people are still, trading on the floor, and they can essentially make trades right there based on kind of the latest information. So this could potentially kind of revolutionize how some of these investment banks basically execute the trades and how they go about essentially doing their business. So that's one example for finance. The same can actually be used, the same kind of Monte Carlo approach can be used for insurance, where basically insurers are figuring out what is the cost, what is the potential cost of insuring a certain type of population, certain type of demographic, a certain type of asset. They still run these Monte Carlo simulations to kind of figure out what is their risk exposure, right? So it's actually very, very relevant for insurance as well. Another use case is kind of the standard imaging use case from machine learning, right? And in this case, it's applied actually to biomedical images. And we actually did this project and did this research with Roche. And we looked at how quantum computers will be able essentially to do some of these biomedical image classification and help us essentially get more information, get a better insights than what we can get today from classical systems that essentially do the same thing, right? And actually, the paper that's out between QCware and Ross talks about how in some cases we can train classical neural nets faster on a quantum computer, and how some of this training can actually be used. We can actually, throughout the training, we can infuse certain characteristics into the neural net so that the neural net is actually fundamentally different from what you would get by doing the classical training on GPUs. And by that, by getting this new neural net, essentially you get different, a different classification of what the algorithm sees basically on these biomedical images. Okay. So the next example is with Boehringer Ingelheim, another pharmaceutical company, and this has to do with the other major problem class we talked about, which is essentially chemistry simulations. So in this case, again, we're looking at how these molecules, how we can simulate these molecules, and how we can simulate essentially proteins, and how we can simulate and predict how easy the protein will essentially form this bond to receptors within the human body, right? And because that's the key essentially metric for a drug, how easy it is for these proteins and the drug to actually bond into the appropriate receptors, because that obviously increases the efficacy of the drug, right? So this is, again, research we published together with Boehringer Ingelheim. Actually, that went on the archive very, very recently, and kind of shows you, again, what can be done on this chemistry simulation field. We've also worked quite a bit with oil and gas, and in this case, actually, with BP, solving essentially this power tolling problem. So this is kind of an energy production and energy distribution problem where you have these counties and these cities essentially going out and essentially buying energy from energy producers. In this case, BP is an energy producer. And so when, these counties or cities or sometimes even states kind of go out and buy a certain amount of power, then the energy producer needs to essentially be able to tell how much it's going to cost them basically to deliver that power. So they need a very good estimate of how much this contract is really worth, and therefore from that price point they can essentially negotiate up and down. But they need a good estimate of how much it's going to cost them to essentially produce the power that's demanded by the county or the state or whoever is essentially buying their power. So power tolling has to do with this kind of energy trading and pricing essentially calculations. Okay, so that's BP, excuse me. So another example is with Total. Here, we worked with them on kind of scheduling different operations within their distillation operations. Maybe when we can put some people on mute, thank you. We also work with Covestro. Covestro is a German chemicals company. They produce products like polyurethane and many others. And together we worked on essentially doing, again, kind of molecular dynamics, figuring out basically how the molecules bond to each other and how we can essentially produce better materials. We've also done work with Airbus, and aerospace is another big field for quantum computing. In this case, we worked on this problem called design verification. So figuring out whether, by changing a certain module within a design of an aircraft, that might affect in a bad way other modules. And if the simulation shows an error, then kind of detect where the error will be across the different modules. We also have done, you can solve the standard logistics optimization, standard supply chain problem. We've done it with this Japanese automotive producer. They produce transmissions, Aisin. So you can see here, so we kind of covered many different sectors, many different industry sectors, and many different use cases, so that you can understand basically what are kind of the real interesting use cases and what are the different industry sectors that are already engaged essentially in quantum computing. So now you might be asking, okay, well, what can I do from a personal perspective or from an organization perspective for my organization, how I can get my organization essentially to start getting ready for quantum computing. And what I'm going to share is basically a roadmap that we've seen time and time again with these large corporations. What typically happens? What are the typical steps to actually start getting ready for for quantum computing, right? So it typically starts by essentially forming sort of a group of like-minded individuals within the organization, right? So forming this internal quantum computing working group, attending a conference, getting some technical and business education. And then typically for an organization, especially a large corporate, it's about finding a partner, right? So all of these topics are very technical, very specialized. So it's good to find a partner that has done this before. It's actually know kind of what are the interesting use cases, have experts that can code quantum computers, can access quantum hardware and so on and so forth to help you essentially execute the remaining parts of this roadmap. And then typically there's some kind of use case discovery workshop or use case discovery discussion to identify use cases that are critical for your organization and near term for the quantum computing space. And then we typically execute some type of pilot project. Then if there are more quantum computing experts on the customer side, we typically execute an advanced project. And this thing can take 2 to 3 years. So, each one and every one of these steps is actually a long step. And this also takes us back to the previous point we made earlier that, yes, quantum computing is a few years away, but for these organizations to get ready, it's actually going to take them several years to get ready, just like it did with their, ML and digital transformation initiative, right? So we're almost kind of ready to wrap here and start taking questions. The one thing that I'm going to leave you with is, remember, kind of this talks about attending a quantum computing conference. And I just wanted to highlight that QCware has been putting up a conference every year in December in Silicon Valley for the last 4 years. So this is going to be kind of the 5th installment of this conference we call Q2B, as in B2B or B2C, right? So the tagline is Practical Quantum Computing. It runs from 7 through the 9th this year in December. It's exclusively in person, and it's at the Santa Clara Convention Center. We just opened up registration just last week, actually, and we're announcing more and more speakers, and we will be announcing more and more speakers. Actually, I just realized I don't have the link here on this slide. So the link is actually q2b.us. When maybe you can put it on the chat as well, or you probably already have done that earlier in the chat. But we'll be happy to see you there. And with that, I'm going to just move to this screen and we can start taking questions.
All right, Yianni, thank you so much for this enlightening presentation. Something I totally understood. A lot of the quantum events I've seen is very, very technical. So this is very, very helpful, Yianni. Thank you so much. Yeah, we do have several great questions here. So I'll go ahead and start reading some of these based on the themes that we have here. Okay. So
Nardo,
one of the
Nardo, before you go, Yianni, do you mind unsharing your screen so we can see
Sure.
each other?
Yeah.
Thanks.
Yeah.
Okay, great. Thanks, Yianni. So the first question we have here is how accurate and how error prone is this quantum computing algorithm?
Yeah, so actually right now, quantum computers introduce errors into the calculations, and that's actually what's holding back quantum computing right this second, right? And holding back kind of the scaling of quantum computers. Most analysts believe this is basically an engineering problem, that over time, engineers essentially will figure out how to make quantum computers less error prone. But right now, that's really, that's kind of the fundamental kind of restriction, that if you try to run a computation if you have many, many steps in your computation, then after a certain number of steps, you'll start accumulating so many errors that your calculation is going to be completely basically disrupted, and you're going to just get random noise at the end. So that's something that the teams like from all these big hardware vendors, IBM, Google, IonQ, Rigetti, Honeywell, this is exactly what they're working on right now, making essentially quantum computers less error prone.
Okay, great. Yeah, I do know that there's a lot of work and innovation happening in this space, coherence times, error detection, error prevention, and stuff like that. So yeah, thanks for that, Yianni. So we have a question here that is more cybersecurity oriented. We have a couple of questions related to this. So it's about the implications of cracking the cryptographic ciphers. And how far off do you think we are in terms of quantum computing breaking the current RSA security standards?
Yeah, so the short answer is we're several decades away, right? So, I mean, you can pick maybe, I think, kind of 30 years away is kind of the average, I think people kind of typically mention, because it will take a huge quantum computer to break today's standards, right? Today's RSA standard. It will take a huge quantum computer that has no errors, right? And that's actually what is pushing the horizon out. So it would require a huge quantum computer that introduces no errors into the calculation to be able to factor, essentially, to do this kind of prime factorization that the standard, that the encryption standard is based on. So we only expect that huge of a computer to only be available and to be error-free in 20, 30, maybe 40 years, right? And actually by that time, NIST is actually already thinking about the next, essentially, encryption standard, right? So by that time, we'll have a new standard that can hold up to the quantum computers, because as we said, quantum computers are good at solving some problems, not everything, right? And so NIST is already now, the National Institute of Standards and Technology is looking at which standard, basically, which new problem to pick that will become essentially the new encryption standard that quantum computers will be just as bad as classical computers at solving.
Yeah, yeah, I have heard a lot about the NIST work, and I think there are also a lot of startup companies getting into post-quantum cryptography, both here in the US and in the UK, that I'm seeing some bit of traction in.
Yeah.
So the next question I'd like to kind of ask here is, so it's related to transitional technologies, right? So is anyone considering hybrid solutions? For example, the quantum algorithm makes a first pass, later to be refined by a digital algorithm. So that probably could mean classical algorithms. So how do you see quantum and classical working together?
That's a great question. And actually, that's exactly what many of the analysts, and we are included there, we think it's really going to take a lot of classical pre-processing to essentially pare down a problem or decompose a problem into like a core problem that the quantum computer will solve, and then pass essentially the information back to, again, a classical system to do a lot of classical post-processing, right? So actually, we expect many of these solutions that we're going to see over the next several years to have a lot of hybrid components, a lot of classical pre-processing, a quantum core, and a lot of classical post-processing. Maybe the only maybe solution area where that might be a little bit different is machine learning, actually. In machine learning, actually, it turns out that I mean, I don't want to go into the details, but you can process maybe one data point at a time through the quantum computer. You can essentially calculate the distance or do like a matrix multiplication that the quantum computer can do really quickly. And then essentially have your entire maybe classification algorithm running on a quantum computer. You'll still do a lot of input output on classical systems, right? I mean, the input output will still be on the classical systems, but you could be essentially executing your entire classification or regression or clustering algorithm on the quantum system. But for, let's say, chemistry simulation, or let's say optimization, there's going to be a lot of back and forth and a lot of sort of, the classical system helping the quantum system and vice versa.
Okay, yeah, I'm excited about that, because I do see some, actually a lot of startups that are trying to connect the quantum computing and classical computing together in some virtual manner. So I could see this happening first, even before, the full-blown quantum algorithms are really getting rolled out. So thanks for that, Yianni.
Sure.
So we have a question here. It's a good one. So I think the question is related to, what do you see as like the hardware limitations of quantum computers, right? So where do you see the issues when it comes to performance and scaling?
Right. So great question. So I guess so there are these fundamental engineering issues, right, on scaling, which have to do with, okay, well, you have these qubits on, let's say, like a superconducting chip, and how do you create like 1 million of those, and still have them kind of retain essentially their performance and kind of their qualities, right? So these are kind of very, very technical and very kind of down to the weeds reasons as to why we haven't still been able to get to that level. So, but just to answer it from a high level perspective, I guess there's how long a qubit retains its information, right? So that's one fundamental area that impacts hardware scalability. And the other one is basically how long or whether a certain operation on a qubit or 2 qubits introduces an error, right? And so there's this thing called the gate fidelity, which we don't even think about anymore. I mean, it used to be also an issue with classical computation, but now we're down to classical operations. They have, you can do like 1 billion operations without an error, right? Now, unfortunately for quantum computers right now, you can maybe get up to 100 operations without an error, but if you get to 1,000 operations, you're definitely going to get a few errors, right? So those are kind of the fundamental sort of hardware limitations that are holding us back right now, and kind of what people are working on.
Okay. So I'll switch. So a lot of big questions right now are quite technical. So I'll switch to a business question one, Yianni. So the question is, what is the risk that quantum goes? Actually, the business question is, what is the rationale to start now? It seems very early. Why not just wait?
Yeah, I mean, it's really a proposition for people that want to essentially hit the ground running when quantum essentially hardware gets there, right? And also keep in mind that, I mean, you don't want to be caught basically just kind of sitting on your hands, right? Especially if you are part of a large organization or a field where maybe someone is going to come up and disrupt you. I mean, we've seen how the banks are reacting to this today, right? And they're getting ready in a very serious way for when this thing will be available, because there's a very significant advantage to being first, right? And also there's a very significant risk to just kind of being very quickly left behind if you haven't built up any capability, right? From now until, you hear in the news, oh, quantum computing is now ready. And you start hiring at that time. You start thinking of how quantum computing will impact you. It's already, it's going to be late already. So, and as I said, I mean, it doesn't take a huge investment. And that's why it helps to think of it as an insurance premium, right? It takes a small investment right now to stay up to speed. So we're not asking anyone to essentially put in like a, multi-million-dollar investment, right? From now until 5 years from now on this, you could say unproven, right, technology, even though we do now have multiple proof points, right? What I'm saying is that it takes a few steps initially with very minimal commitment and capital to stay up to speed, right? So it's basically a small investment to avoid a very large loss, right?
Yeah. I think one of the areas that I think would be a bit of difficulty for a lot of enterprises, Yianni, is definitely in the area of resources, quantum engineers and quantum scientists to basically hire and get as part of their companies.
Exactly. Yeah. And the other thing I tell people is think back to what, with how difficult it is to hire, data scientists maybe, 3-4 years ago, right? I mean, when there was really like a huge need and a huge lack of that skill set, and essentially the same is coming for quantum computing.
And I think it's maybe even a little bit more farther than that too, Yianni, because I don't think I've met any quantum scientist that's not at least a single PhD. I've seen double and even triple PhD type people in this space. So it'll be interesting how this thing plans out. There are several questions here related to, how will quantum change, how we should think about quantum algorithms, right? Or quantum programming. It sounds like we have a lot of technical folks here, and they're interested in learning about,
Right.
what is the difference between what I do in my AI programming now versus what quantum can bring from a QML or quantum deep learning or something like that.
Yeah, I mean, it's frankly, it's kind of like night and day, right? It's basically there's no concept of like an if then statements or for loops or things like that are kind of the basic kind of coding blocks are completely different, right, on the quantum computing side. And so it's kind of completely different really coding paradigm, right, where you kind of have to even relearn the basics. And yeah, I mean, people, have to complete sometimes, graduate level courses, right, to be able to start coding and coding effectively, right, a quantum computer, right? So I'm not saying you shouldn't do it. I think it's actually a great career path, right? Back during kind of the heydays of which we're still living, right, of ML and AI, right? I think there was this article, or there was this article saying, data scientist, the sexiest job on, the 21st century, right? Pretty sure they're going to have a rerun, the next 5 years with quantum engineer being the sexiest job in the 21st century, because there's going to be a huge need for this skill set, and there's actually very few people that currently have it.
Thanks for that. So here's another good question. What do you think shows more promise, universal quantum computers or non-universal approaches? For example, like D-Wave, which is, I remember, it's more on the annealing side, right?
Yeah, good question. So D-Wave, has this special hardware, and my background is in optimization, right? So actually, when I first got involved in quantum computing, we only had D-Wave to work with, right? So we work with D-Wave quite a bit, and I still think there's a future, right, where D-Wave will be able to solve some problems and will provide a performance advantage. I still think that's true. And there will be other problems where the gate-based computers and the universal computers will be, better suited to solve, right? So it's not going to be one or the other. I think D-Wave with the quantum annealer, they're going to find kind of their niche, essentially use case and problem class, and they're going to essentially solve that really well. And then, the other universal computers are going to do other use cases. So it's not either or, right? I think it's going to be both of them at the same time.
Okay, gotcha. Here's another good question related to more on this software development side. Are there any quantum computer simulator that software developers can play with?
Oh yeah, actually there are plenty, right? So I would urge you maybe to go to IBM Q. They have, I think, one of the most popular simulation tools out there. Google and their solution called Circ also has a simulator. Amazon Bracket, which is the Amazon Quantum solution, also has a simulator, and Microsoft has one. So every large company, every large technology company is in this game now. And actually, simulation is one of the things that everybody has, because even though quantum computers are accessible today, so you can code something up and fire it off and through the cloud get it to the quantum computer and get the result back. It's harder, it's actually more costly, you might get noise, and so the result might not be what you were thinking. But with the simulators, maybe you can simulate noise, maybe you can turn off the simulated noise, you can see what the real solution is going to be, and get a lot of traction, a lot of skills and experience through that.
Okay. Here's another business question, Yianni. As a business executive, where is the best place for me to get education on quantum that is in a more simplified manner?
Yeah, so actually, our conference is really at a high level, right? So the Q2B conference is really at this high level business conference. where we have talks from people like BCG, and I think my son is going to make an appearance now on our. Sorry about that. Okay, so just getting back, I guess. So
he'll think of classical computing as the old.
Yeah. So I was saying the conference is actually business in nature, right? So, or business for business people, right? That's kind of the main audience. Especially the first 2 days, you're going to hear from consultants like BCG, McKinsey, Accenture, Deloitte on what they're doing, and you're going to be hearing about the market and how it's moving. And the next day we have kind of the basically all the major vendors like IBM, NVIDIA, Google are going to be talking about, Honeywell, IonQ are going to be talking about their programs, roadmaps. So it's basically like this kind of high level education with the possibility to talk to a lot of the different vendors and kind of get, a lot of perspective like that.
Okay. Another good question related to quantum computers. Is there anyone working on different materials that are possibly usable in making these quantum computers?
Yes, very good question. So actually, I think that's actually the charge of one of the new DOE quantum computing centers. I forget exactly which one, but that's kind of the directive for one or two of the DOE centers that are focusing on quantum computing is basically to make new materials, right? New, semiconductors and other shielding materials, right? For that will be required for the hardware vendors, and that's an area that I believe is going to keep growing. I mean, these kind of engineering concerns, I think, will essentially persist.
Okay. Thanks. So, folks, we are past 6 p.m., but you guys are welcome to stay on for a few more minutes. For those who wants to stick around, and Yianni would be, he's willing to stick around and answer a few more questions if you guys are staying, okay? So another good question here, Yianni. When you consult with a company on quantum algorithms, who provides the resources? Are you running the programs on Amazon, IBM, and Google?
Yes, when we do the consulting, when QCware does the consulting, yes, we provide essentially the experts, and it depends. You can look over the expert's shoulder, and the expert essentially executes the program. And typically, we charge the customer for the computing resources. If we're running on hardware, those hardware resources can be pretty expensive. So it's typically essentially rolled into the price of the project, how much we expect to essentially get charged for the hardware resources. And that's typically something that our customer, our client covers.
Okay. Okay, so another question here related to fusion. What is the risk that quantum goes the fusion way, quantum fusion? 10 years away, 50 years away?
Yeah, so I guess the good thing, I mean, there's always a chance of that happening, but I think the good things that so far the time frame has been shrinking, and has been shrinking quite significantly, right? So I think when you ask some of the sort of full-time professors, right, for quantum computing hardware or quantum computing computer scientists, if you ask them, hey, 20 years ago, would you have thought quantum computers to be possible and practical and, ready in production? People would have just laughed, right? I mean, there was basically no companies building quantum computers. I mean, not an ecosystem, nothing like that. That was 20 years ago, right? Then about 10 years ago, we started having things like D-Wave came around, right? And they built their quantum annealer, and IBM announced their lab, and kind of the fact that they're building some qubits in the lab. Google announced their own lab, and the fact they started building qubits as well. And so at that point, people said, oh yeah, maybe it's like 50 years out. Right. And 10 years down the road today, we showed the time frame, right? We said, well, for some applications it's 2 to 3 years out, for some others it's 5 years out, right? So we've come a long way, and kind of the time frame keeps improving. And what has actually happened very recently is that these hardware vendors have released roadmaps. So now we can hold them to their word, right? So we can say, okay, Mr. IBM and Google and IonQ, those are the three that I've actually released the roadmaps. Here's kind of what you said last year about how many qubits you're going to have and kind of how big your system is going to be and all of that. And here's where you are today. So now it's getting to the point where it's kind of very easy to kind of keep track of the time frame and see whether it's kind of slipping, whether we're staying static, or whether we're accelerating.
Yeah. So what companies do you think will lead the way in providing quantum computing units, or maybe qubits?
So on the hardware side, I mean, I don't want to. I mean, we as QCware, we are on the software side. We're partners with pretty much everyone on the hardware side. I don't want to pick. I don't want to pick a favorite. I'm going to say that IBM is very commercially minded, right? And there are a few other companies that are very commercially minded, and I think they're already putting machines out there. And they're getting a lot of traction, right? So IBM, IonQ, Honeywell, those are the ones that are essentially making commercial systems available today, right? And I think they have a very fair chance of essentially, being around for years to come and kind of delivering essentially good commercial systems. There are many others though that are just beginning, right? I mean, there's now other technologies that are being explored for quantum computers, like atoms, cold atoms, photonics, and others. And so I think right now it's very hard to pick a winner. I mean, I think that's what's going to happen on the hardware side, is that you're going to have kind of this constant kind of leapfrogging and kind of jockeying for a position of who's going to be kind of the who's going to be better. I guess you're going to have kind of the whole VHS Betamax thing, happening on different dimensions. Or maybe I should have said Blu-ray. What was the other one? I forget now. Blu-ray and the other one. But it's going to be very hard. I mean, frankly, I don't think anyone can really kind of predict this in a good way, right? In a safe way.
Right.
Who's going to
well, we should give a plug to Doug Fink's Quantum Computing Report website. So if you guys have not been to his website, I remember that he has a report that compares from qubits, from a qubit perspective, all the different hardware vendors that's currently out there. So Quantum Computing Report, it's a good resource for you guys to look at.
Yep, good point.
Yeah. So another question here is this one is more healthcare related. How could quantum computers improve mental health results by mental health professionals?
Mental health results by mental health professionals. I think the key use case in healthcare, which is related to this, I don't know if this is going to be the one for mental health, but I think it's basically personalizing treatments, right? Based on, first of all the volume of research that gets published on different healthcare domains. Sort of consuming that. Already there are solutions that do that, right? There are kind of classical machine learning solutions that do that, consume basically the papers that are coming out, and then look at a certain, patient profile, and then they, match this patient profile with all the research that is out there, and then they essentially recommend a personalized treatment, right? So I think so this is already, as I said, happening with classical machine learning tools today, classical ML and AI tools. And I think quantum will act as an enhancer of all the classical ML and AI techniques and use cases. And I think that's where it's going to plug in and provide an advantage and an improvement.
Okay. Thanks, Yianni. Yeah, I think we still have a few more questions, but I think it's about 6:10, and we'd like to wrap this up. So I'd like to thank Yianni Gamvros from QCware, for enlightening us about getting ready with Quantum. Also would like to thank the audience here in terms of attending. I hope you guys got something out of this. We will be posting when the recorded links, right? So we will be providing that over to everyone. And I think, Yianni, there's also a question related to the presentation deck. Are you willing to provide that to the folks as well?
Yes, happy to do that. So we'll definitely do that. Mm-hmm.
Okay. Any last words, Yianni?
Thanks for giving me the opportunity. Yeah, please let me know if you have more specific questions and you want to have a kind of more one-on-one chat on your organization and how to get started. Happy to help.
Okay. Thanks a lot, Yianni, and thanks a lot, everyone.